Okay, we're on the section of the principle of mathematical induction, often just abbreviated PMI. All right, so again, what I'm going to encourage is that you listen to the lecture, you try to follow the examples that are being presented to you, then study that material, the stuff we present to you, that is the lecture material, and we do provide the notes to you, and the examples, and then do the supplemental exercises. And after that entire section is done, section 15, then you do the WebAssign. All right. So just to give a brief overview, they're really kind of short lectures, although I will say it's a big topic. Certainly it does take a little bit of thinking on your part to understand what we're presenting to you. And this is what's called the proof technique. And I'm just going to read this to you. And again, we'll go over the notes later. And again, the reminder is there's little tiny videos on the side. If those videos are helpful, we would encourage you to watch those little short videos. All right. I basically just repeat the stuff during lecture anyway. But anyway, it says let Pn be a statement. Now, this is going to be a statement involving positive integers n. All right. Now, what does that mean? Like 1, 2, 3, 4, 5, so forth and so on. All right. Then they go on to say P1 is true and, right. So if you can do this, if you can show that P1 is true and you can show the proof of the general statement PK will eventually follow to PK plus 1 for every positive integer k. Right? And this is the tough part for students to get. Why would we do this? The point of doing this is what we're basically saying is if P1 is true, and then I can show that PK leads to PK plus 1, what am I doing? I'm showing 1 would lead to 2, and then 2 would lead to 3, then 3 would lead to 4, then 4 would lead to 5, so forth and so on. All right? So again, it's a simple proof technique. What I mean by that is a proof technique that's pretty simple to follow. On the examples that we present to you, though, now I want to point out it may not be so simple on the examples we're not presenting to you. So we only present very simple examples. Now, of course, when I say simple examples, they'll follow this verbatim. We're going to show P1 is true, then we're going to write down PK. We're going to also write down PK plus 1. But what we're going to do is work from PK to PK plus 1. All right. Once we do that, we're going to say the proof is done. All right. So I really think, it might be, hard to, for some students to do because the algebra involved in it. But I do want to point out the algebra gets really sticky. You're going to move toward using what's in a computer algebra system to do it. And we'll show that as we go through this section over here. But here's the deal. The reason we go through mathematical induction is that we want to show that these formulas are correct. Now, what does this first one say? The sum of the integers from 1 to n, right? Sum of the integers from n is a really simple formula, just simply n plus 1 over 2. And we've seen that one before. And the sum of the squares, 1 squared plus 2 squared plus 3 squared up to n squared is this formula over here. Now, when you get to Math 121, which is Calc 1 at Essex County College, you would have to know certainly the first formula and the second formula. It would be nice if you knew the third formula as well. What does that one say? The sum of the cubes, 1 cubed, 2 cubed, 3 cubed, all the way up to n cubed would be equal to this statement over here, right? Now, again, I'm going to say like, I4, I5, sum 1 to the 4th, 2 to the 4th, 3 to the 4th, up to n 4th. That form is a little complicated. We can actually prove it though. My intent is not to memorize that. I wouldn't want to memorize that either. My intent is to prove it. Now, granted, as you go through mathematics, the other intent is, how did people come up with these formulas? All right. Now, I hope you remember, we came up with formula 1. We did that in prior. All right. These other guys, how do they come up with those? And there's interesting ways of doing it. But right now, we're not so interested in coming up with these. We're interested in verifying that they're true. All right. Then what are we going to do? All right. After we do that, we're going to work through examples. All right. We're going to work through examples. As we work through these examples over here, it might be tough. All right. It may be tough. But the intent of working through the examples over here is so you can then do what's called supplemental activities on your own without assistant. Here's the problem though. If you've not studied and understood what we presented to you, going to supplemental activities or WebAssign, in my opinion, is a waste of time. You need to do some exercises before you get to these supplemental activities. What are the exercises? Thinking about what we're presenting to you, watching us do examples, and then repeating those examples. And then after that, you go to some activities. The sub-activities, I want to point out, when you're looking at those over here, They do have little footnotes, and I want to tell you why they have footnotes. The reason for the footnotes is they're giving you a hint. And what's the hint? Here, you probably want to use a calculator to do the manipulation. Now, when I say calculators, you might be surprised by this, but even those dinosaur calculators, the T89, are capable of doing expansions, all right? That's where most people get into trouble, is in the algebra. They can do symbolic algebra. What are we using now? For the most part, I want to encourage the use of Sage code. So if you look at the Sage code that we're presenting to you, hopefully will be understandable. All right, so I want to briefly go through by switching the screen to the whiteboard. And I'm at the whiteboard now. I'm hoping you can see that. And certainly we're in section 15. Now, what I want to do is just go to the next page. And what I want to talk about is just looking at these formulas over here and, and talking about, what they are. So let me write this down one at a time. And these formulas would need to be known when you get to Math 100. So let me write down the first one. The first one says this: the sum I equals 1 to n is equal to 1 plus 2 plus 3 plus 4 plus yada, yada, yada up to n. And what's that equal to? Well, according to what they're telling, we've actually derived this one before, n plus 1 over 2. Now, certainly if you use PMI, and we'll go through it certainly when we get to examples, but I want to point out the first thing to do is write down P1 with the understanding that this is P. This is our proposition up here, right? We're making this statement up here. Now, whether it's true or not is incidental. I want to write down P1. Now, what would P1 be? Well, if I wrote it down, what would it look like? It would look like this. I equals, by the way, when I say PPN, I equals 1 to 1, I. This would just simply be starting at 1 and stopping at 1. And what do I got there? What's n now? It's 1. 1 plus 1 over 2. Is this a true statement? Well, what's that? The top would turn to be 2, the bottom would be 2, and that would give me 1. That's certainly correct. P1 is definitely correct. Now, someone's going to say, well, then I'll see if P2 is correct, and I'll see if P3 is correct. No, what we want to do is write down PK. Oops, sorry about that. And what does PK look like? Well, whoops, sorry about that. I can write down PK here. I equals 1 to K, I. What would that look like? 1 plus 2 plus 3 plus dot, dot, dot up to K. What would that equal? Well, I'm looking at the formula, K plus 1 over 2. Now, what I'm going to do over here is I want this to collapse. When I say collapse, go towards. I want it to go towards PK plus 1. Well, this question is, what's PK plus 1 look like? Let me write that down for you. That would look like I equals 1 to K plus 1, I, and that would be 1 plus 2 plus 3 plus yada, yada, yada. Now, sometimes where does it stop? It stops at K plus 1. So I get to K eventually, and then I would get to K plus 1. And what would that equal? And push this up a little tiny bit. Well, I'm plugging in K plus 1 in the formula. And again, if you don't remember the formula, look back over it. The first thing is going to be n. Well, now it's not n, it's K plus 1. And what's the next thing going to be? Well, it's going to be that n, which is K plus 1 plus 1. All over 2. All right, I'm going to simplify a tiny little bit, not too much. What would this equal? K plus 1, K plus 2. All right, so this is general structure. If you can do that, you're doing really, really good. All right, now here comes the problem. What we have to do now, and we're not going to do it until we get to examples, we have to take this, work with this to make it look like this. And I'm going to say that should be fairly easy to do. And how would I do that? I would add K plus 1 to both sides of the equation. Your job now is to show that the left side, this is the left side, is this left side, and this right side, which is the whole thing over here, is that right side. By the way, that's a one-directional operation. We're going from PK, and we're trying to get to PK plus 1. And that's the general structure. So how could you accomplish that task? Well, quite simply, it's done through algebra. And again, we'll go through examples. So let me just take a look at another one, and I'll point out what the structure is. And the structure, I'm just kind of pulled to the side. And I want to just look at this one here. Let me pull this one over to the side, get rid of this stuff over here. And again, we're not doing it. We're just talking about what the structure looks like. All right. So I want to tell you what the structure looks like. The first thing I'd like to write down is, what does PN look like? What does PN look like? Well, PN, this is the proposition they're giving me. They're saying the sum from I equals 1 to n of I cubed. Well, what does that look like? 1 cubed plus 2 cubed plus, I'm just copying by the way, 3 cubed plus yada, 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 up to n cubed is identical to this statement over here. All right. Now you might say, where's that thing coming from? I wouldn't worry about that. What I'd worry about is, what's the proof technique? What's the first thing you have to write down? You have to write down P1. Now, wherever I see n, I'm going to put 1s. That's pretty simple to put down. That's I equals 1 to 1. And that's going to be I cubed. Well, I start at 1 and I stop at 1. So that will be 1 cubed. Is that the same thing as, let's write this down. And again, the n is 1 now. That would be 1 plus 1 over 2. I hope you realize what you get over there. If you look at it, you would get, 2 on top, 2 on bottom, and that would be 1. And 1 squared is 1. And what's 1 cubed is 1. So I'm going to say this is definitely correct. All right. Then what do you do? Well, I can't say this enough times. You're going to follow the process. The process is writing down PK. What's that going to look like? I equals 1 up to k. This is going to be I cubed. What does that look like? 1 cubed plus 2 cubed plus 3 cubed plus yada, yada, yada up to k cubed. And what would that equal? Well, I'm looking at the formula. It would look like k plus 1 over 2 squared. Now let me point out what I'm saying over here. I know P1 is true. So I know this is true for at least for 1. I'm not going to test it for 2, by the way, but I know it's true for 1. So what I want to do, I want 1 to lead to 2, and then 2 to lead to 3, and then 3 to lead to 4. And I hope you realize we could be here all day doing this. We just need to show it in general. So what are we really trying to show? We're trying to show PK plus 1 now. Whoops, sorry about that. What does that look like? I equals 1 up to k plus 1, I cubed. And then, yeah, it takes time to write it down. And what does that look like? 1 cubed plus 2 cubed plus 3 cubed plus yada, yada, yada. Now you'd eventually get to k cubed, and the next term on would be k plus 1 cubed. All right. Let me push this a little bit over, okay? All right, go back over here. And what's that equal to? Well, I'm looking at the formula. So what's the formula say? It says it would be k plus 1. That's what I'm doing over here, plugging in the factor k plus 1 for k. And what will go over there? Well, it would be k plus 1 plus 1. And I think I can do that. And what would that give me? K plus 2. All over 2, quantity squared. Now someone says, how could you go from this to this? Well, that looks pretty simple to me. I would say all you have to do is to both sides of the equation add k plus 1 cubed to both sides of the equation. And these are things you learn in really low-level algebra, that if you have an equality, if you add the same thing to both sides, it remains to be an equality. And here comes the trouble. This is the left side, and this is the left side. Your goal is to show this. Now, by the way, that's the easy thing. They're clearly the same thing. Here comes the tough part. This is going to require algebra. This is the right side, and we want to show this. And the only way to do that is by using algebra. Certainly, we will go through examples, but here's the deal. Let me repeat this. When you get to math 121, you're going to have to use these sum formulas to prove other things. So this is going to be foundational. And when I say it's foundational, again, a lot of people look at this and say, I don't think I could ever remember that. Through use, you can. Right? So I'm going to say, this one we did already. We've actually, derived that one. We gave a little story about Gauss doing it. This one over here, we really haven't seen that yet. But when you get to 121, some teachers say, oh, you have to memorize the formula. And I would say, yeah, probably through use, you probably should memorize it, at least temporarily. All right, this one over here, easy for me because it's related to the sum of the integers. These are the integers cubed, by the way. These over here, no one's going to ask you to memorize that. I also want to point out another problem with these things over here, that these things can be quite tedious to manipulate. All right, and this one over here, really tedious to manipulate. All right, we talk about using computer algebra system, those guys over there. The first three, though, I want to, again, emphasize to you over here is when you get to Calc 1, this should be known, this should be known, and this should be known. And you should be able to readily do that. All right, what do we do next? I'm going to point out what we're going to do next is we'll do those examples one at a time. We'll just do the examples. All right, now as I go through the examples, again, you might be confused, but that's where study department comes in. You go back, you review what's been discussed. You can rewatch the videos if you like at the end of the week. These little embedded videos, you can watch them as often as you like. All right, they're short and they're easy to watch. Right, whatever works for you though, including going to the internet, including Khan Academy, and doing PMI. All right. Now, if you're taking another course at kind of college, like, discrete mathematics, I'm pretty sure they'll be doing PMI, as should your computer science teachers. And they should also be going through PMI, which is the principle of mathematical induction. All right. Thank you.